So we will start today with the LPG unit. First, I would like to share with you a safety moment. So let's talk about a little bit about LPG bottles. I don't know if for you, but here in Europe, it is very common to use these LPG bottles in our kitchens. Electricity here is very expensive, so we use a lot of these LPG bottles for our kitchens. This LPG stands for liquefied petroleum gas and is a common fuel source for heating and cooking. LPG bottles are safe when used correctly. When using LPG gas cylinders, you have to always ensure adequate ventilation and never use indoors or in confined spaces. Always read the manufacturer operating instructions. Do not connect or disconnect bottles near a naked flame. Do not use LPG in windy conditions. Always keep bottles cool and away from flames, sparks, and heat. Only use approved or certified hoses and connections designed for gas. Never use homemade ones. Okay, we have seen several accidents when these bottles are not properly handled. So these are some of the precautions that you have to take when handling this type of bottles. Why this safety moment? Because we are now going to talk about LPG in the Carvala refinery. So let's start with our unit, LPG unit. The content of the presentation today, we will see the LPG production unit in Carvala refinery scheme. We will see, of course, the purpose of the unit, the incoming and outgoing streams, the feedstock, the products, the simplified block diagram, the process theory and chemistry, and the main process variables in the unit. So let's start. Let's see our refinery scheme. We have seen already all these units. Okay. Remember, we have the crude oil, we have the distillation unit, the vacuum distillation, and all these units mainly to produce gasoline. And we also have these middle distillates, kerosene and diesel. And last week we saw this asphalt blowing unit. Today we will see the LPG unit that you can see here at the left. The LPG unit will receive a stream for the continuous catalytic reforming unit, the naphtha hydrotreating unit, and the polynaphtha unit that we have seen for the gasoline production. It is not it's an open art unit without a licensor, and this is the capacity, the production capacity. Okay, that is 10,950 barrel per stream day. So what is the purpose of this unit? In this unit, we have two purposes. Okay, we first have to remove H2S from the LPG stream coming from the naphtha hydrotreating unit using the ethanolamine solution. And our second purpose is, of course, to separate the stream into propane and butane. So this stream coming from the naphtha hydrotreating unit, once we have removed the H2S, will join the LPG from the polynaphtha and the catalytic reforming unit, and then resulting stream will be stabilized and split into propane and butane products. Here you have the H2S that we will remove, And here we have the propane and the butane. Propane being the 3 carbons and butane 4 carbons. So let's talk a little bit about the LPG highlights. The liquefied petroleum gas, it is also called LPG, GPL, gas, is liquid petroleum gas or simply propane or butane. It's a flammable mixture of hydrocarbon gases used as a fuel in heating appliances and vehicles. It is increasingly used as an aerosol, also propellant and a refrigerant, replacing chlorofluorocarbons in an effort to reduce damage to the ozone layer. When specifically used as vehicle fuel, it is often referred to as autogas. You can see in some gas stations they have this autogas also referring to LPG. And here typically you can have this LPG in different proportions of propane and butane. So LPG can be 100 propane or 60% propane and 40 butane or 35 propane and 65 butane, depending on the country and region. Also depending on the season. In winter more propane, in summer more butane. We will see the specifications that you have for the LPG in Carvalho refinery. As its boiling point is below room temperature, LPG will evaporate quickly at normal temperatures and pressure, and is usually supplied in pressurized steel vessels, as we have seen in the safety moment with the LPG bottles. So it is important to be clear that LPG can be have different definitions, always referring to propane and butane, but it can be in different proportions. Remember that whenever you have a question, you can ask, raise your hand, or you can write in the chat. So, which are the main incoming and outgoing streams? Also, always referring to case one, the data it is taken from the material balance that we have for this unit, that is unit 11, LPG production unit. As we have said in the purpose of the unit, we have two main sections within the LPG unit. We have this section, that is this section we will treat the LPG from the naphtha hydrotreating unit. And then we have this fractionation section where we will get our propane and butane. So if we see here in this first section, we have the LPG from the naphtha hydrotreating unit with H2S in this stream. So how we will get rid of this H2S? We will treat it with the lean amine solution. And then we will have here the LPG from the naphtha hydrotreating unit without H2S. And we will have here our rich amine. And then we will have here the fractionation, this stream, and these two other streams coming from the CCR and from the polynaphtha unit. We will go to the fractionation unit and we will get our propane and butane. So this is the main incoming and outgoing stream for the LPG unit. Which are the characteristics of our feed? We have the LPG from the naphtha hydrotreating unit. Remember, LPG, it is mainly propane C3s and C4s. Of course, we can have a little bit of lighter components and of heavier components, but the main components of a LPG stream should be propane and butane, or C3s and C4s. Okay. So in this case, you can see the components of the LPG from the naphtha hydrotreating unit. As you can see, we have here the main components: propane, isobutane, and N-butane. Of course, we have here some lighter components and some heavier components. In this case, the LPG from the naphtha hydrotreating unit, we have almost 3.5% for this case, so we have to decrease this value. That's why this stream is first treated with lean amine to absorb the H2S. We have the LPG also from the CCR and the polynaphtha unit that we will send directly to the fractionation section. And this is the composition of this LPG from the CCR. The same, you can see that the main components, there are the propane, isobutane, and normal butane. And with the LPG from the polynaphtha unit, you see, yeah, you have the propane, but you have also some uh, trans 2 butene, cis 2 butene, isobutene. So you don't have also only alkanes, but you have also alkenes that are part of this LPG stream. Remember that in the polynaphtha unit, one of the purpose was to also to have some double bonds formation. So these are the stream. These two streams will go directly to the fractionation section in the LPG unit. Which are the product specifications? The we need to have less than 50 ppm of H2S. We need to have less than 0.5% more of C2 content of lighter components. And for the propane, we need to have 2% maximum of C4. And for the butane, we need to have 2% maximum of the C3 content. These are the product specifications. LPG around the world include mixes of propane and butane. I will tell you that this mixture of propane and butane in the Carvala refinery, it is done in the, you will see it in the tank farm operating manual. So it is part of another module that is the blending module, when you will see how the different intermediate streams are blended to to have our final products. Okay. Propane has a low boiling point, so it's more suited for colder environments. It evaporated at more or less minus 42 at atmospheric pressure. And the butane doesn't burn well at lower temperature. It evaporates at around 0 degrees centigrade at atmospheric pressure. Carvala LPG blending system has been sized to produce winter LPG quality that is 60% molar propane and 40 molar butane, or summer quality that is 40% propane and 60% more butane. So you have the proper installations to have this blending in the tank farm unit. But the product from for us today in our presentation, the products are propane and butane. Okay. Then in the tank farm, the appropriate pumps and storage tank, you have this LPG. Okay, so let's begin with the process description. If you have questions about the products and the feedstocks, okay, so let's start with the first slide of this process description. As we have seen, first we have to process the LPG coming from the naphtha hydrotreating unit to remove the H2S. Remember that in this naphtha hydrotreating unit, we have removed the sulfur, but we have converted to H2S. So we have to now to decrease the content of H2S. How we will decrease the H2S content? We will treat it with amine, with an absorption process. So the LPG coming from the naphtha hydrotreating unit will goes to this naphtha hydrotreating LPG amine absorber, where we will put in contact with the lean amine from the amine recovery unit. Okay. The amine wash LPG is sent here. We have already treated this LPG, so the stream will go to this LPG amine settler in order to remove some amine by adding water. Why do we have this settler? Because in this stream you can have some amine that you have used to absorb the S2S. So the idea here is you remove any traces of amine that you can have in this stream, and you use water also to help to separate this amine that you can have in this stream. So the LPG H2S content is lower from about 2.7, 2.9 to less than 50 ppm to meet the product specification. As we have seen, we have this specification for our product. Okay, so in this process, we have decreased the H2S content from this percentage, more or less, to 50 ppm. Then this LPG from the amine treatment session is collected with the LPG from the polynaphtha unit and from the catalytic reformer unit, and will be sent to the de-ethanizer. So we have this stream that we have already treated in this amine absorber, and we will mix with the LPG coming from the CCR and from the polynaphtha unit. This receiver here, it is has two functions. It's like a feed drum, and it's also the overhead receiver from this for this column for the ethanizer. Okay. In the de-ethanizer, as the name said, we will
Sorry,
remove.
Pilar, the voice is very low. Please,
Okay,
just raise your.
perfect. So in this de-ethanizer column, we will remove the lighter components that are contained in the LPG. Okay, so in this column, the volatile compounds contained in the LPG, hydrogen, methane, and most part of the ethane are stripped off, and the product maximum ethane content of 0.5 is achieved. Remember that we have seen also this is a product specification to have less than 0.5 percent mole maximum in the product. How we will achieve this specification with this the ethanizer. Okay. Of course, we will get this lighter component stripped from the ethanizer, and we'll go to the amine recovery unit that we will see later. So here we have already decreased the content of the lighter components of the LPG streams. Now we will have to go to the propanizer column to continue with our process. So this is the first section. We have treated this LPG from the naphtha hydrotreating unit in an amine absorber. We have decreased the H2S content, and then we will mix this stream with these two other streams coming from the CCR unit and from the polynaphtha unit. In this first column, we have decreased the lighter components content, and then now we are going to the propanizer column. So the stream coming from the de-ethanizer is sent to the propanizer column to split the LPG into propane and butane. Remember this our product from this unit, propane and butane. Vapor that leaves the top of the columns are sent to the condenser and then return as reflux. The excess condensate is sent to the battery limit as product. So the top of the column, we will get our product and we will send to the storage. Remember that in this case, the propane, we have done a specification of maximum 2% of C4 content in this stream, okay? And in the bottom, the product, we will get our butane product meeting the required specification of having 2% content maximum of C3s, okay? And we will send to storage, okay? In these cases, of course, we will send to the tank farm unit, and for this propane butane, we have a special tank that are bullets where we will storage our propane and butane to be further blended to get the LPG product. Okay, so we have seen that this de-ethanizer bottom we will send to this column, to the propanizer column, and here in this column, we will separate propane from butane, okay? Propane being lighter than butane, it is in the top, and the butane at the bottom of the column. This column is 30 has 30 trays, and it operates more or less at 14 kilos. We will see now the PFDs to see some of the operating condition of these columns. So this is the process overview for this unit. Let's see more or less the
Question, Pilar, sorry, just one.
yes,
Yes.
Yes, sorry, Bilal.
yes, yes, please.
I'm asking about this material in which phase, liquid phase or gas phase?
We will handle this in liquid phase. Okay, we will pressurize to have the chance to operate at liquid phases.
So the butane and the propane
Yes, are liquid.
are liquid. Okay, thank you.
Yes, yes. So which is the main process theory that we have in this unit is of course the absorption of hydrogen sulfide from LPG with the diethanolamine. Remember, we have already seen some of these processes. It is this reaction. You react with H2S and you have this compound. Here you have this formula that it corresponds to the ethanolamine, being there this ethanol radical, okay, here, and this another ethanol, and this is the ethanol amine, okay. So when you see this R, it is one of these radical component, the ethanol, okay. The absorption here takes place in two liquid phase for a column. Is not as we have seen in another cases with gas liquid. In this case, is liquid liquid. Okay, the lighter sour LPG flowing upwards through the filled column with this solution, the ethanolamine. If we see the characteristics of these two streams, you will see that the LPG that we will treat in the amine column is a very low density compared with this solution. So it will help to have this absorption. The LPG that lives at the top of the absorption column will contain some small quantities of the ethanolamine, partially due to entrainment, partially due to the slight solubility of the ethanolamine in the LPG. And then we will separate by water washing and going to the settler that we have seen in the process description to separate some of this solution that we can have in the LPG. So the LPG obtained from the various units in the refinery contains some light compounds that are very volatile and will create an unacceptable high pressure in the storage tank for the LPG. And that's why we remove these light ends by stripping in the deethanizer column. Okay. So the idea here is that you should know that in this unit we have this absorption in liquid phase in the column. We have this settler to remove some of this deethanolamine that you can have in the LPG stream. And of course that we have to remove the lighter components, and we will do it in the ethanizer column. Okay, this is the amine that we will use in this unit with a specific concentration. We will see now in the operating variables. And remember that this is the ethanol radical and is the amine, so we have the ethanolamine for this unit. Of course, this we call it here when we don't have H2S in the amine, we call it lean amine, and then we have this rich amine. In the following sections, we will see how we will again remove the H2S from this rich amine, and we will convert again in lean amine. Okay, but this is the idea of these solutions, is that they get absorbed the H2S in the solution. So the main process variable for this section, we have of course the LPG flow rate, the LPG hydrogen sulfide content, the LPG temperature, and this solvent flow rate. The lean diethanolamine flow rate, it is the only operating variable that can be changed in the LPG absorber column when the hydrogen sulfide content is higher than desired. Linamine circulation must be increased. Of course, you have to take care of this lean diethanolamine hydrogen sulfide content, the solvent concentration, the temperature, and the hydrogen sulfide content. Water, we have also provisions for some water makeup. When the amine concentration in the wash water is higher, we must pump condensate, and we will ensure that we have the correct amine concentration. Okay. We will see here that the temperature in the absorber, we have seen that the main equipment that we have in the unit is the absorber for the LPG coming from the naphtha hydrotreating unit to remove the H2S. So the temperature on the last tray of this absorber is a result of mixing temperature of two fluids and the exothermic heat of absorption. Okay, remember that we have this absorption is a slightly exothermic reaction. In this case, the idea of this slide is that you have to take care that you have very high temperatures in the absorber, okay, because you can have some vaporization of the LPG, okay, and this vaporization will disturb the operation of the absorber. Remember that the absorber in this case for the LPG unit, it's worked in liquid phase. Okay, so we must avoid higher temperatures because we can have some vaporization of the LPG. Okay, so this is the idea of this, and that is in your operating manual. Yeah, you have to take care. Now, I would like to, if you don't have questions, we can go to the PFDs to see some of these operating variables and to see the PFD of this unit.
We have one question, Pilar.
Yes, please.
Sorry, Bilal, if I am asking question too much.
No,
Uh,
please.
about the absorber, amine absorber. Why it must be in liquid phase? We have at isomerization unit we have a scrubber. We wash the gas by caustics and we get it sweet gas. Why we not make it the feed of the absorber? Why it's not the gas? Not why it's liquid?
Yes,
And
because we are treating here not of gases, but we are treating a liquid stream coming from the naphtha hydrotreating unit. Okay, so in the
so
case that Yes. You have you say that we have, yes, there are different ways also. Remember that we have saying also in the polynaphtha unit we have the hot caustic wash of the stream, but for this stream they have selected to have this amine absorption, and this is in liquid phase because we have this advantage of having at, if we work at higher pressure, we have this stream as liquid, and we want it as liquid to mix with the other stream coming from the CCR and from the polynaphtha unit, and that's why they have decided to
So
this.
you mean the efficiency of separation will be better if
Yes,
the
in
feed
this case for
is in
this
liquid
type of a
phase.
stream. Yes, in this case for the type of a stream that we are handling, that we have a liquid stream at some pressure, of course, it is better for the this amine absorption. Of course, they have evaluated
So if
other scenario, but they have decided to have this amine absorption to reduce the
so
H2S content. Yes.
it's not possible if the LPG was a gas and we use amine as a shower and on counter currents, so we can take the H2S. Is that possible? If we
Well,
use amine as a shower, steam
Yes, in
yes,
like
another unit
scrubber.
استاذ. Yes, in another unit. Sorry بلال.
yes, please.
استاذ we have عندنا وحده رقم 16 مختصه بالاوف
Yes.
غاز. اوكي يونت 16.
ها
يونت
يعني
16
استاذ ما نقدر
مختصه بالغازات
ندخل
استاذ.
اي
هاي الوحده
يعني
مختصه
LPG
بالLPG
هو بالحالة
كسائل.
الطبيعية يعني
سائل استاذ سائل بالحاله الطبيعيه
هو
خليط السي
غاز
3 والسي
إذا
4
نقدر نسوي له
تحت الضغط. تحت الضغط هذا شنو هو؟ سائل. اوكي. اكو وحده ثانيه مختصه بالغازات، وحده رقم 16 راح نشوفها الاسبوع الاخر. هاي وحده نقطه. النقطه الثانيه ليش دا ينضغط وننزل الحجم؟ هذا راح نضغط الحجم لحدود ال 240 مره. يعني المتر المكعب الواحد مال LPG عادل 240 متر مكعب كفيبر مال خليطهن سي 3 وسي 4. سمعتني استاذ؟
يعني على
واضحه؟
الكمية.
كميه
نعم
بالضبط حتى نقدر نعامل اكبر كميه ممكنه من الماده في اقل
أكبر
حجم.
كمية ممكن نعالجها.
اوكي.
أوكي
واحنا ايضا المستخدم
تمام.
يعني في الاسواق العراقيه انت شايف غاز عندنا بالقناني غاز سائل صحيح؟ صحيح؟ بالقناني مال الطبخ
صحيح
غاز سائل. احنا
أي.
نريد ننتجه كسائل ما نريد ننتجه كغاز، لان ما عندنا احنا انابيب وشبكه مثل العالم. اكو دول تستخدم الغاز الطبيعي هذا العادي تستخدمه كشبكه للطبخ وللامور.
اي هسه بالضبط
احنا
قال استاذ عدي هسه احنا الغاز يجيني بالبيت يجي غاز
بالضبط
سائل
غاز وليس سائل. نعم
بس انت اذا نفس مثل ما قلت تفضل استاذ عدي يعني الكميه نفسها اللي تستهلكها بالسائل اذا تحولها غاز يحتاج لك مثلا افرض تريله حتى تستهلك نفس الدبه مال الغاز اللي عندنا اياها. ليش؟ لانه من بالليكويد هو مو نفس الحجم من هو غاز اكيد يعني.
نعم LPG 240 ابو يوسف بالضبط 240 او 260 المتر المكعب
بس
الواحد.
بهالحالة هم راح أخسر يعني تكلفة معدات إضافية حتى أسيل
طبعا
الغاز
مجبور لازم استاذ مجبور عليها
وأحافظ
طبعا.
عليه سائل.
مجبور عليها اكيدا مجبور عليها. وعندك بروسس كامل. اكو وحده معامل اسمها غاز الشمال وغاز الجنوب شركتين. يعني ذن هن سبب مشكله كل المشاكل العراق بالكهرباء من وراء التقنيه هاي. يعني هاي التقنيه لو عندنا احنا ما عندنا اي مشكله بالكهرباء. فلانه لايسنس صار وتقنيه كلش غاليه ف لحد الان الجماعه ما ادري ليش ما جابوها. على كل فمو موضوعنا هذا. موضوعنا انه احنا نتعامل هسه كسائل استاذ. سائل كله سائل. هذا الحكي كله سائل والفحوصات كلها سائل. ازا ليكويد يعني لان النتائج تختلف بالكثافه وبالامور. كله ازا ليكويد بالجي اس يسموه غاز كروماتوجرافي ماكو. كله ازا ليكويد. اوكي استاذ ازا
يعني هسه
رقم
هو
11.
السبب الأساسي إنه هو الفصل
نعم.
حيكون أكثر كفاءة ومعالجة
بالضبط.
كمية
اكبر واحنا نريده اصلا منتج كسائل.
وبالمنتج أريده ليكويد.
انا اريده كليكويد لانه انا دا اتعامل وياه كليكويد كوقود للسيارات وللطبخ. اوكي،
شكراً
وكل ازا
أستاذ
ليكويد، يعني وحده رقم 11 ليكويد استاذ، وحده
أوكي
رقم
أستاذ.
16 ازا غاز، ان شاء الله راح نشوفها غازات وايضا نعاملها. شكرا استاذ.
Thank
ثانكس
you for
بلال،
that.
ثانكس فيري ماتش.
No, thanks to you.
ثانك يو بلال.
Okay.
Thank you.
So we have seen here, do you see the PFDs? Yes, no?
Yes, yes.
Okay. So we have here our inlet, okay, from the naphtha hydrotreating unit. We say here that we have the liquid stream, and this is with more or less 2.7% more of H2S. We have here in blue and dark blue the ethanolamine solution that is 25. It is important to have the proper percentage of the solution. Okay, 25% for the ethanolamine, and we have here the absorber, and we have 15 trays in the absorber. We have lever controller, and we have here the outlet with the settler. Remember that we have said that here at the top of the absorber we can have some amine. So we have this settler to remove any amine that we can have in our product. And we do it also with water due to the solubility of the ethanolamine in the water. It will prefer to go with the water than with the LPG. So we have this settler, and we have our product here without H2S, the red line at the top, and then we will mix with the other two streams, the LPG from the CCR and the LPG from the polynaphtha unit. And we will see send to this vessel that is the VOO2, that is a double purpose. We have seen it is like the feed drum, and it also serves as the overhead drum for the deethanizer column. That is the TOO2, okay? So, in the bottom of the deethanizer column that we use a reboiler, as you can see here, the EOO2 with the steam, we get this stream that we will send to the depropanizer, okay? The lighter components from the deethanizer column we will send to this recovery unit. We will see in the following presentation. The rich amine, that is the dark blue from the top, from the bottom of the absorber, has now more or less 1.8% of H2S, okay? This rich amine that we will send to the amine recovery unit. This is the first PFD of the unit. So here we have the absorber, that is the tower, the column 001, where we remove the H2S, and we have also this column, this TOO2, that is the ethanizer column. Okay. The other slide PFD of this unit is this one. We have another column that is the depropanizer column, where we have split our product coming from the deethanizer, and we have the propane at the top, the green, and at the bottom we have the butane. In this case, you can see that we are working around 14 kilograms in the column, and in this column we have 30 trays, and we have our stream green. It is the propane. When we say propane, it is not only propane, as we have said, we have also some butanes, but according to the specification, we cannot have more than 2%. And we have lighter component, but very small quantities of lighter. And we have butane at the bottom, and also here we have some propanes, but we have to guarantee that we don't have more than 2%, and also we have some heavier components. these streams, the propane and butane, they are sent to the storage tanks, where we have also in the tank farm, as we have said, all the installations to produce the LPG for the blending of the propane and the butane. And remember that this butane also we will use it in our gasoline blending to adjust the vapor pressure. So this is another use of this butane, okay? So the product of this unit are propane and butane, and the LPG itself will be produced by blending these two products, and we will have different specification for winter and for summer, as we have said in the product specification.
Sorry, Bilal.
Yes.
Bilal, if you could back to the first slide before that one.
Yes, this one.
Yes, this one. From the high pressure receiver drum or top, there is a stream, liquid stream. It must goes directly to the splitter.
Which
Bilal.
one? This one you say, the
No,
settler.
high pressure receiver drum, not the settler. The high pressure, yes, there. Yeah. The high pressure, so this is the black one. Yes, the black one is the liquid.
This.
Yes, this one. Yes, yes.
Yes.
It must where it goes. It must goes directly to or back
to the column, to the detonator.
to the detonator. Okay, okay.
Yes.
Okay. To be sure to separate
yes.
all the light component.
Yes, and these light components will be
So,
as of gas to the
okay.
yes.
Yes, to the south. So the feed for the splitter is just from the bottom of the detonator.
Yes, from
Okay.
this.
Okay, this red one. Yes,
Yes,
thank you very much.
this red one goes to the depropanizer.
Okay. Because I didn't see all the picture from my mobile.
Yes,
It's cut from the bump.
Okay, this one.
Okay, thank you.
Yes. These are the LPG detonator feed pumps. This
Feed pump, yes, yeah,
P002AB.
Yes, I didn't see it before. Okay, thank you, Willa. Thank you.
So you have here this is the feed to the column, because
Yes,
this
the continuous recycle this
yes,
liquid is be sure it's remove all the lighter
all
component.
the lighter component. Yes.
Yes, okay. Thank you. Thank you very much.
We've got another question, Pilar, from Mr. Haider.
Please.
Yes, Mr. Haider.
Hello, everyone. Actually, I would like to know why would we separate propane and butane in this unit?
Yes, because we have said that the LPG product that we want to get from Carvala, we have two specifications, one for winter, one for summer, and of course we have other uses for the butane in the refinery. So the idea is that you have separated propane and butane, and then in the blending section, you can adjust this proportion between propane and butane to have your final product, your LPG product.
Okay, thank you. And one other question is that in the DEA solution stream, the DEA represents only 25%. So
Yes.
what is the rest?
Water.
Okay, thank you so much.
Yes.
You finished, Pilar, with the...
Yes.
Okay, so I think that's the end of the LPG unit, right?
Yes.
So what we suggest, I think we take maybe 20 minutes break and then we come back to the gas sweetening. What do you think?
For me, it's okay. I don't know for you.
استاذ عدي اوكي ناخذ 20 دقيقه
اوكي استاذ اوكي حبيبي
كيفكم تريد 5
اوكي
خليه تصير 25
مضبوط يلا مضبوط
اي خليه 25 minutes
اوكي
يعني 12 ونص قبل نرجع ماشي
اوكي
12 ونص
لا 20 باس
12 و20 ماشي اوكي 12 نقوم نصلي اوكي ويوسف شكرا حبيبي
اذا تردون وقت اكثر خليها اكثر ما عندي مشكله بس
لا عادي حبيبي هاي بعد وقت ماشي
ماشي.
اوكي حبيبي.
Hello. Okay, guys, I think we are ready to go now. Pilar, you can resume the presentation. Thank you. Mm,
Yes, now.
Yeah, now we hear you. Yeah.
Yeah, yes. Okay, now we will see this gas sweetening and the sour water stripper. Uh, First, I would like to go through the safety moment related with acid rain. In the unit that we are going to see today, we will remove H2S from the off gases. And one of the reasons, if we don't want to send these off gases to burn, because these off gases will be used in boilers and furnaces and will be burned and we will create some SO2. So what is the acid rain? We can say that a sulfur is an element commonly found in crude oil and petroleum products. Sulfur is considered an undesirable contaminant because when burned, it generates sulfur oxides. Okay. When sulfur oxide combines with water and air, it forms sulfuric acid, which is the main component of acid rain. Acid rain can cause deforestation, acidify waterways to the detriment of aquatic life, and corrode building and materials and paints. Consequently, most finished petroleum products have a limit on how much sulfur they can contain, making sulfur removal an important point of the refinery process. So you can see here in this drawing at the right that when you generate from these industries, you generate sulfur dioxide and nitrogen dioxide, and then it will mix with water. It can create the sulfuric acid and nitric acid, and you have the acid rain or acid snow, and of course it can create this deforestation. So that's why it's so important to have a proper sulfur uh, treatment in our refineries to remove the sulfur as much as it can in the treatment processes. So how to avoid the acid rain? Of course, to reduce the emission of pollutant gases by industry, encourage the production and use of renewable energy instead of fossil fuels, reduce the energy consumption of factories and companies. This is also an economical, of course, evaluation that for all industries it has to be done to reduce the energy consumption. Promote innovation and new technologies aimed to optimizing energy consumption and developing renewable energy. Plant trees to absorb polluted air and make the population aware of the importance of reducing household energy consumption. Encourage the use of electric vehicles and no other polluting vehicles such as bicycles. Well, and remember that in our case there is no planet B, so we have to take care of our planet for the next generations. So this is one of the main reasons for these units that we will see now, to reduce the H2S content in the off gases coming from the different units in the refinery. Mainly due to these environmental problems, and also, of course, from the equipment point of view, it can cause corrosion, can cause problems in our equipment in the refinery. So let's start with the gas sweetening and sour gas stripper. The first, we will see the gas sweetening, and then we will see the sour gas strip, the water stripper. So in the gas sweetening, And amine regeneration, we will see this during the presentation. We will talk about the unit capacity, the purpose of the unit, the incoming and outgoing streams, the feedstock, the products, the simplified block diagram, the process theory and chemistry, and the main process variables. As you can see here in the title, you see gas sweetening and amine regeneration. So in this unit, we have these two purposes. We will have the gas sweetening, and we will also regenerate the amine, okay, that we have used in the different units and also in the unit in this gas sweetening. So, but let's go slide by slide. And if you have questions, please, you can ask. So, we are talking here about this unit that is shown here in this refinery scheme in blue. Okay, we see here GS, that stands for gas sweetening, and the ARU, that is amine regeneration unit. And you have here the capacities. The capacities for the gas sweetening, it is 13,470 normal cubic meter per hour. And for the amine regeneration unit, that is a liquid, you have two trains, and this capacity 317 standard cubic meter per hour. Okay, so this is the capacity for this unit. So the purpose of the gas sweetening amine regeneration unit is the treatment of the different refinery sour gases in order to produce sweet fuel gas according to the specification, where we will use these sweet fuel gases in furnaces and boilers. We will use this, so we will burn these fuel gases. And during the burning of these fuel gases, we have to avoid the production of SO2 to avoid the acid rain and problem with the equipment corrosion. And also in this unit, we will have the regeneration of the rich amine coming from refinery unit. Remember that we have seen in different units that we use lean amine to absorb H2S, and we produce rich amine that has the H2S in the solution. So in this unit, we will regenerate this rich amine to transform again to lean amine. Okay, so we will see also this regeneration in this unit. So two purposes, treatment of the refinery sour gases and regeneration of the rich amine. So the unit therefore consists of two different process sections. We have this gas sweetening and the amine regeneration. The amine regeneration section will have two identical trains. Each one is 50% of the whole amount of rich amine produced in the refinery. Okay. So we will see now the incoming and outgoing streams, also referred to case 1. We have the absorption section. As you can imagine, in this section, we will absorb the H2S coming from the different stream of gases from the different units of the refinery. And in this regeneration section, the rich amine will be transformed again in lean amine. If we see the different streams coming to each section, we have the sour gases for the different units. You have the crude distillation unit, the naphtha hydrotreating, this kerosene and diesel, the vacuum gas oil, and the LPG that we have just seen. We have the sour gases coming here and going through the absorption section. In this absorption section, we'll have linamine that goes into a column and it will convert it in ricamine, and we'll have our sweet fuel gas that it can be sent to our network of fuel gas for the different users in the refinery. So this is the first section here in purple. It is the absorption section. So we have the different gases from the different unit. We have here H2S. So we have to remove H2S. How we will remove H2S? With linamine, and we will get this ricamine and the sweet gases. In these gases, we don't have H2S, or we have, but we have a limit of H2S. And in this ricamine, we will have the H2S that we have absorbed here in this section. But we have also some other streams of ricamine from other units where we have made also this absorption process. So we have also ricamine for the diesel hydrotreating, from the LPG, from the vacuum gas oil, from the FCC, and from the crude oil, crude distillation and vacuum distillation unit. So we will mix all this ricamine with also this ricamine, and we will go to the regeneration section. In the regeneration section, we will get again linamine. We will eliminate the H2S that we will have here in the ricamine. But where it will go this H2S? It will go in a stream of acid gas, okay? So here we have the H2S that we have here, and this stream we'll see next week will send to the sulfur recovery unit, and in this unit we will produce sulfur from the H2S that we have in this stream. So this is more or less the idea of the unit. We have two sections, absorption and regeneration. In the absorption, we will eliminate the H2S from these streams, and we have our sweet fuel gas that we will use for the different users, furnaces, heaters, boilers in the refinery. And then we will regenerate the ricamine to have again our linamine and send it back to the units. And we will have this stream, the acid gas, that will contain the H2S that we will send to the sulfur recovery unit. That is another unit inside the refinery where we will produce sulfur. Okay, that is another product of a refinery. Remember the sulfur. Okay. So we will see now some of the characteristics. We will go through some of the characteristics of these streams that are coming as a feedstock to the unit. So the feedstock to the gas sweetening, we will see here, maybe it's a little bit confused, but we will see here the feedstock to this section and the feedstock to the regeneration section, okay? So the feedstock to the gas sweetening, that is the first section. We have the off gases from the different units, and you can see here that we have quite a high concentration of H2S of the off gases from the crude distillation unit, vacuum distillation unit, from the naphtha hydrotreating. We have also off gases. Of course, this data you can find it in the process design basis. This is the unit 16 in the refinery, that is the gas sweetening and amine regeneration unit. Oops. Okay, we have also the off gas from the kerosene diesel hydrotreating unit. You have a hydrogen H2S content, of course, from the vacuum gas soil hydrotreating unit. And you have these of gases from the LPG. So these are all the feedstock for the first section, that is the gas sweetening section. And we have, of course, also the other section of the unit that we have the amine regeneration. In this amine regeneration, our feedstock are the different rich amines from the different units in the refinery. We have the rich amine from the diesel hydrotreating. This is the H2S content. We have the rich amine from LPG. We have this rich amine from the vacuum gas soil hydrotreating unit. From the FCC, also some CO2. And from the crude distillation unit and vacuum distillation unit. Of course, you can see it more in detail, all this specification in the process the same basis for the unit. So far we have seen feedstock for the gas sweetening that are off gases coming from the different unit with high content of H2S, and we have seen the feedstock to the second section of the unit, that is the amine regeneration unit. We have seen different rich amines coming from the different unit that we have seen also we have H2S in the amine. The off gases, of course, there are gases, and the rich amine, there are liquid streams coming to the amine regeneration unit. What we want to get from this unit? Which are the specifications for our product in this unit? As you can imagine, we'll have two specifications, one for the sweet fuel gas and one for the lean amine that we will get from the unit. So the sweet fuel gas, it must contain 50 ppm maximum of H2S, and we call it sweet, okay, because we don't have H2S. And for the lean amine, we have this H2S plus CO2 mole per mole of the diethanolamine, 0.02 maximum content. Remember, lean amine, it is said when we don't have almost H2S, and rich amine when we have the H2S in the solution. So we have these two product specifications from the for the unit. Okay, the sweet fuel gas and the lean amine specification. So let's see how we will get our sweet fuel gas in the unit. So these the gases coming from the different units, you can see here from the fuel distillation, for the naphtha hydrotreating, for the kerosene diesel hydrotreating, from the vacuum gas soil hydrotreating, and from the LPG unit. It will go to are mixed and sent to the knockout drum, integrated at the bottom of the amine sour gas sorber, where possible condensate are separated and discharged to the acid flare. Here we have a column that has integrated a knockout drum, and then if you have some condensate, you can send it to disposal to the acid flare. From the knockout drum, the gases enter the bottom of the absorber, so the gases will go here to this amine sour gas absorber, where most of the H2S is removed by absorption with the lean diethanolamine. So you can you put some lean amine, and you will get your rich amine with the H2S. The sweet gas that we will get from this absorber is sent to a knockout drum that is also integrated in the absorber top in order to remove any entrained amine and discharge to the refinery fuels unit. So we will send it to another knockout drum here that is also in the same column integrated, and then we will have our product sweet gas that we will send to the fuels unit that will have a maximum of 50 ppm volume H2S. The rich amine is sent to the amine regeneration section that we will see later, okay? Antifoam in this unit where you work with the amine, it is very important to control the foam formation, so we inject antifoam in different points. This foaming is causes what here you have the antifoam injection by the presence of particles. We can have some degradation product for the amine that can create foam, so we have to avoid this foam formation. So we inject antifoam in this point in this unit. Okay. So this is the main idea of the gas sweetening. We have all this stream, we mix this stream, we go first to this knockout, we'll separate if we have some liquid, and then we will go to the absorber where, as we have seen in many of the absorbers that we have in the refinery, we mix, in this case, gas with the liquid amine, and we will go to this knockout drum also integrated with the column where we separate and we will get our sweet gases. And in this knockout drum, we will have, if we have some amine that is with our product, it will be discharged and mixed with the rich amine from the absorber. This rich amine, it will be sent to the regeneration section. So the second section of the unit, remember, is the amine regeneration. So let's see how we will regenerate our rich amine. So the rich amine enters in the rich amine source drum where hydrocarbons as well as some sour gas compounds such as H2S and CO2 are flashed and separated. So the rich solution is preheated before to be fed to amine regeneration, where the amine solution is stripped out of the acid gases. So heat is provided by the amine regeneration reboilers by LP steam. Let's see the regenerator. It is here. So it is here the rich amine. We will preheat it, and then we'll be to the go to the amine regenerator. How do we strip? We will use a reboiler with LP low pressure steam. So the heat will be provided with this reboiler. Hot acid gases and steam are cooled down and partially condensed. We have here the top of the regenerator. We cool and partially condense. Acid gas leaving the reflux drum flows to the sulfur unit. Remember that we have said that here in this stream we will get the most of the H2S that we have in this solution. So we will produce sulfur. We will see it next week how we will transform this H2S into sulfur, into elemental sulfur. So a portion line facility for this continuous portion of a portion of the regenerated reflux has been provided. So we can pour to the sour water stripper when we have a accumulation of some product. So we pour some of this water. Remember that this solution has a lot of water, so we have a lot of water here. And the lean amine that is go from the bottom of the regeneration, it will flow through these heat exchangers and then to different coolers and filters, and we will send as lean amine. So this amine regeneration is based on a stripping, of course, with heat. So we will strip the acid, the H2S from the rich amine that we have here. The H2S will be sent with the acid as an acid gas, of course, with the acid gas to the sulfur recovery unit. And the lean amine that we have here, it will be cooled down and filtered and then sent as lean amine to the different users, to the different units. Okay. So this is the idea, more or less, of the amine regeneration section of this unit. So let's see again. Again here, we will see the same theory, the same reaction as we have seen in the LPG unit. Okay, because we are using the same amine for the off gases, we will use this, the ethanol amine, that is a secondary amine that removes the H2S and the CO2 from the hydrocarbon streams. And the reaction between the amine and the acid gases can be established as follows, as we have seen in the LPG unit. We have the amine and the H2S, and we will form this rich amine containing the H2S. As you can see here, if you see this reaction, you have 1 mole of the amine and 1 mole of the H2S, and you have the formation of 1 mole. So you have a low pressure because you are going from 2 moles to 1 mole. So the absorption reaction is favored by high pressures. Okay, this is something that you have to know also. And it's a slightly exothermic reactions. Okay, the absorption process. So remember, the absorption process are favored by high pressures and low temperature. So if you want to go the other way, you will go with low pressures and higher temperatures. That is during the regeneration. Okay. If you have to go the reaction in the other way, you will work at lower pressure and higher temperature. That is said here. No? The reaction is reversible and the equilibrium can be shifted by regulating the temperature and by changing the partial pressure of H2S. Low temperature and high acid partial pressure favor the absorption of acid gases into the amine solution, as we have said. And as the acid gases absorb into the amine solution and react with the ethanol amine, heat is released. Okay, so it is exothermic. This heat release causes a temperature rise, which can be significant in the solution as it passes through the absorber towers. So this is the absorption reaction. This is exothermic and is favored by higher pressure. we have seen, okay, this reaction in other units. What happened in the regeneration? So in the regeneration, we will work with high temperature and low pressures to favor the acid gas release from the solution. To regenerate the amine solution, heat must be added to remove the acid gases from the solution. Heat must be supplied to the regenerator reboiler to provide adequate stripping steam in the bottom of the regenerating tower and to heat balance the regenerator. Heat balancing the regenerator requires supplying heat equivalent to the heat of the solution plus the sensible heat needed to raise the solution temperature, okay, to the desired bottom temperature. Well, this is a heat balance around this regenerator. And as we have said, the process of regeneration is carried out at low pressure and high temperature. So if we perform the absorption at high pressure and low temperature, so if we need the reverse reaction, we will need to work the regeneration at low pressure and high temperature. So here we can see some of the main process variables that we have in this unit. We have some specific values that we have to guarantee. That is this quantity of the mole of H2S by mole of the ethanolamine in the resolution. We have here for the lean solution also a quantity, a 0.02 mole. We have here the concentration of the amine, 25% by weight. And we have here the temperature. This is desirable to operate the regenerator at the lowest practical temperature to minimize degradation and corrosion. We can, of course, the reaction is favored at these high temperatures, but we cannot go to further than this because otherwise we will have degradation of our solution that will cause corrosion in the system. So we have to be very careful with the temperature. And it's usually advantageous to operate the regenerator at a pressure as low as practical to minimize the temperature in the tower and thereby reduce corrosion and amine degradation. Pressure and temperature, the pressure that it will work in the regenerator, it will give you also the temperature that you need to have a good stripping in the regeneration. So it is good to have as low as practical pressure to minimize the temperature that you require and then to avoid this degradation of the solution, okay? That it will cause corrosion in the system. The regenerator reboiler heat duty must be enough to provide adequate degree of amine regeneration and H2S desorption from solution. Also here we have these other process variables. The absorber temperature, we need lower absorber temperature at a given acid gas partial pressure favor absorption reaction since it's exothermic. Higher pressure improve acid gas removal as we have seen in the absorber. We can lose some amine, So you must be replaced to maintain the optimum concentration. It's important to minimize these amine losses because it's also money that you have to replace this solution. And it's important also to have the appropriate water balance. We have to remember that we have seen that we have to sometimes to purge a portion of the regenerator reflux due to these compounds that you can have in the top. So you need to purge to control the level of these components that can cause corrosion. And then you have to also to have into consideration the water balance. Okay, if you need to put more water or to have the proper uh, solution concentration. I think that I have said a lot of things, but we didn't have too much time for this unit. But we can see it now in the PFD, the process of this unit and some of the operating variables. So we can also overview again the process of the unit. If you don't have previous questions.
Guys, do you have any questions so far? No, you can proceed.
Okay.
No.
You see here the PFD, Ahmed?
Yes, yes.
Okay. So here you have remember that we have said that in this unit we have two main sections. We have the absorption, the gas sweetening, and then we have the amine regeneration. So let's see the absorption. I will put it a little bit bigger. Okay. So here we have the absorber. Okay. Here this tower, it is the T001. The unit is the 16. So we have the absorber, and you can see that in the bottom you have a knockout drum, and in the top also you have another knockout drum integrated with the column. So you have in green the different streams, the sour gases stream that it will enter the absorber. Okay, we have here the quantities, the kilograms per hour, and the H2S that you have in this stream. It will go first to the knockout drum located at the bottom of the absorber, and then it will go to the absorber where it will treat it with the lean amine, and you will get the rich amine that is the purple. Our product of the column that we want, we will send it to the knockout drum that is at the top of the absorber. This here, we have here some the misters, and then in orange or whatever color is it our sweet gases that we will send to the fuel gas, to the refinery fuel unit. We have here we have according to the case one, we have the 37 ppm volume of H2S in this stream. So lower than the 50 that is the product specification. In the column, you will have some online analyzer, as you can see at the top, that it will tell you the H2S content in the sweet gases that we will send to the refinery fuel system. This the absorber, you need this linamine that you see here, that it comes to the top of the absorber. Okay. The rich amine that we get from this absorber, okay, that is the purple line at the bottom of the absorber, it will it will be a mix with the rich amine from the different units that we have here from the diesel hydrotreating, the LPG, the vacuum gas oil, the FCC, and the crude distillation unit, vacuum distillation unit. All these rich amine, the purple lines, will be sent to the amine regeneration. Okay, here we have two streams because remember that for this unit we have two trains with the equal capacity. Okay, so this is the absorption of the unit. Okay, and then we have, well, here also you have the tank. Okay, but of course the amine storage tank. Okay, and then we see also this in the unit we have the regeneration of the rich amine. Remember that we have now to remove the H2S from this rich amine. How we will do it? We have this rich amine that is the purple stream, and then we will go to this regenerator, that is this column that we have here, that is this TO 201, that is here. This is the regenerator. Okay, so at the top of the regenerator we have our acid gases. Okay, the gases that will contain the H2S, and we will send to the sulfur recovery unit here. Okay, here we have our H2S in this stream. Of course we will have all the lighter components, but the main, as you can see here, this stream is 4,418 kilograms per hour, of which 4,000 is H2S. And here at the bottom of this regenerator, we have the red line that it will have this lean amine. Okay. So these are all the calculations that I have put also here. Remember that they have said that we have to have these quantities in the lean amine. So this is a calculation. Okay. This is the H2S plus the CO2 divided by the amount of the solution. You have this quantity. And also, you can see here, the concentration, it is 25, okay, of the diethanolamine divided by the total quantity of the solution. It is 25% of diethanolamine. And here also, if you see the stream 20, if you go to the material balance and you go to the stream 20, you see here that you have this diethanolamine and H2S. So if you divide it, you have here the quantity that is specified as another important operating parameter of the unit, the moles of H2S divided by the mole of the diethanolamine. So this is more or less the the unit. Okay, it is quite important. Also remember that they have set the temperature to keep it 131. You have here the temperature at the bottom of the regenerator. It is important not to go higher than this temperature because you can cause degradation of the solution, and it will cause problems of corrosion and foaming in the system. Okay, this is more or less what I had prepared for this unit. So it's important. We have the two sections. Okay, we have this first, the absorption for the sour gases. We will produce from this first section, we will produce sweet gases that can be sent to the different users in the refinery, mainly heaters, furnaces, boilers. How we will get this sweet gas? We will pass through this absorption column. We will use linamine to absorb the S2S content of these streams. This we will have from this bottom of this column a rich amine solution where we will have the H2S that we have absorbed from these streams. We will mix this rich amine with the other rich amines from the different units of the refinery, and then we will send it to the amine regeneration unit. What is the purpose of the amine regeneration unit? It is to transform this rich amine that we have in purple into lean amine. How we will uh, achieve this? We will strip the H2S that we have in the solution. We have this reboiler that you see here. This reboiler, it will heat and will send, it will strip, and we will have the H2S now here in the top of the regenerator. And this H2S we will send to another unit in the plant that we will see next week. That is the sulfur recovery unit. And then we will get some sulfur. That is also another product from the refinery. And at the bottom of this regenerator, we get our linamine without H2S that can be used again in the different units. Okay. So this is more or less what is about this unit, this gas sweetening and amine regeneration. If you have questions.
Let's check. Any questions, clarifications on the gas sweetening unit? Okay, it's very quiet today. So, okay, what I suggest, we take maybe 15 minutes of break and then we come back.
Okay, perfect.
Because you have only the sour water stripper left, right?
Yes.
And it shouldn't take long, right?
No, no, no.
Okay, so welcome back, guys, to the last part of the presentation today. So we're going to talk about the sour water stripper now. So Pilar, you can resume the presentation. Thank you.
Yes. So we'll talk now about this unit, the sour water stripper. The content of the presentation is the sour water stripper unit capacity. We will talk about the purpose of the unit, the incoming and outgoing streams, the feedstock, the product. We will talk about a simplified block diagram. We will see the process description, the process theory and chemistry, and the main process variables. So this is here we have the sour water stream stripper unit. This is the capacity. We have 2 trains, and the capacity of each train is 63 standard cubic meter per hour. Okay. So the purpose of the sour water stripper unit is to remove H2S and ammonia from the refinery byproduct water in order to reduce it in several units of the plant or dispose to wastewater treatment used for further treatment. Remember that when we have seen the different units in the refinery, in some cases we have seen sour water to treatment, and this is the treatment. So this is where we will treat all these waters coming from the different refinery units. So here the sour water coming from the crude distillation unit, naphtha hydrotreating, kerosene, diesel, and vacuum gas oil unit is collected in a common header and sent to the sour water strip unit, train 1 and train 2. This, in some cases, this sour water that come from the FCC for the sulfur recovery unit and from the amine recovery unit, we send it only to the train 2 because it can contain some contaminants such as phenol, cyanide, CO2, etc., and is collected in an independent header and sent to this train 2 only. Okay. Well, so some like refreshing, what it means phenols. This is a phenol that is a compound consisting of one or more hydroxyl groups bonded to an aromatic hydrocarbon group. So when we talk here about these phenols, is this type of molecule. And we talk about these cyanides here. It is that contain this group, carbon nitrogen and a triple bond. So it is important that these streams that come from these units, we will send it to this train only because the final use will be different than from this one. So that's why we separate this stream that come from this unit. So the sour water stripper is composed of two independent trains treating each 50% of the total sour water produced in the refinery. The train 1 is designed to process no phenolic, you cannot contain phenols, sour water, and the train 2 is designed to process phenolic sour water. Part of the produced non-phenolic sour water is sent to the second train. So let's see more or less the incoming and outgoing stream for train 1 and train 2 for this unit, the sour water stripper unit. So in this case, we have the sour water from the different units. This sour water, non-phenolic, can go either to train 1 or train 2. And these that are the phenolic, that can contain all these very hard contaminants to remove, as we have seen, the phenol, the cyanide, can go only to train 2. From this, we will use this strip water. We'll send it again to the different units. And here, we'll send also, we can send it to the wastewater treatment unit. In the case of this water that we will produce in train 2, we will send to the first unit, to the crude distillation unit, vacuum distillation unit. Here again, we have some sour gas that we will use in the sulfur recovery unit. Okay, we have seen in the previous unit that the acid gases goes to the sulfur recovery unit. Also, these gases that we will get in these trains, we will send it to this sulfur recovery unit. That is another unit inside the refinery. So 2 trains. Some of the streams can go only to this train because they have different destinations, okay? And this here we have district water that can go again to the units or to the waste. It is WWT stands for wastewater treatment inside the refinery. We have here also the quantities. These are kilograms per hour. Have a lot in this crude distillation unit, and also in this hydrotreating. And we have here also this small quantity of sour gases that goes to the sulfur recovery unit. But we will see more in details now the feedstock and the product of the unit. So remember that we all only talk about this case one. It's such an example of the feedstock that we have. So we have this quantity of sour water from the crude distillation vacuum distillation unit, and here you have the ppms of H2S and ammonia that we have in these waters. We have again also the sour water from the kerosene hydrotreating unit, the quantity and the content of H2S and ammonia, also from the naphtha hydrotreating unit, from the diesel hydrotreating unit. This also, you can find it in the process design basis for this unit, that is still the same unit that for the gas sweetening is the unit 16. Okay, so, and here we have more, all the waters that you have from the different unit. Here you can have the difference of the water that comes from the FCC unit that has all these phenols and cyanides, and that's why this water we will send only to the train 2 of this unit. What is the product that we want to get from this unit? Is a water with less than 10 ppm of H2S and less than 10 ppm of ammonia content in the water. So let's see more or less how it is the process description of this unit. So the sour water from the common header enters the sour water stripper feed drum, where possible traces of liquid hydrocarbons are separated. Possible flash gas from the feed drum is sent to acid flare or to the sulfur recovery unit. Here. Sour water from feed drum is sent to the sour water stripper feed tank. The tank is designed with 3 days of residence time in order to homogenize the feed to the sour water stripper, to remove remaining hydrocarbon and assure a more stable operation. From the tank, you will send it to the stripper. In the case of the tank, the sour water feed tank, it is blanketing with hydrogen, with nitrogen, and the outbreathing of the tank, it is sent to the incinerator in the sulfur recovery unit. So this tank is not an atmospheric tank. It works a little bit at slightly higher pressure. And if to keep the proper pressure, if the tank is connected with the nitrogen, we call it a nitrogen blanketing. When you put nitrogen in a tank to keep it in this way, air will not enter the tank. So you keep like a blanket of nitrogen in the tank. In case you have an overpressure, a slightly overpressure in the tank, these gases we will send to the incinerator that we have in the sulfur recovery unit. So the purpose of this nitrogen blanketing is to avoid the air inlet to the tank. Of course, in other cases, you can have also nitrogen blanketing for safety reason, for product contamination reason. Okay, so you can have here that you have nitrogen inlet, and if you have an overpressure here, you can send the off gases to the incinerator that is in the sulfur recovery unit that we will see next week. So this first step is to mix the different sour water from the different unit, and you go to the stripper feed tank, like to have time to homogenize all these waters before we send it to the stripper. The sour water from the feed tank is fed to the stripper after being preheated against the column bottom product. So we send it to a heat exchanger, and then we send to this sour water stripper. In the sour water stripper, the sour water is passed downwards while the upward flow is stripping steam that will remove the H2S and ammonia. We have here a boiler that works with low pressure steam. A pump around is provided to condense vapors in the column top trays, reducing the amount of water which saturates the overhead sour gas feeding the sulfur plant. Because here we will send this off gas to the sulfur recovery unit, so we don't want to have a lot of water here, so we cool and send these vapors down again, condense and cool to the bottom of the column. So this overhead that it contains H2S, it will send to the sulfur recovery unit, and the water, that is stripped water that we have here, we have to cool this stream before we send it to the user or to the wastewater treatment.
We've got one question, Pilar, here.
Yes, please.
Yes, Mr. Carlo.
Hello, everybody.
Hi.
I just want to ask Ms. Pilar about the previous slide
Yes.
about the slope water, slope oil, sorry.
Yes.
Yeah. We know that the water density is higher than other liquids, so how the oil in the bottom of this feed drum?
Yes, we will see in the PFD the arrangement of this drum that have like a compartment for the hydrocarbons. We will see it now. Yes.
Yeah, just wait
So,
until we open the PFD.
Okay. Yes, yes.
So it's not by gravity.
No, just wait, just wait.
Yes,
The answer will come to you when we
Yes.
review the PFD.
Yes.
Okay, thank you.
Because you cannot take details from a block diagram. Block diagram doesn't
Yes.
tell you much.
Thank you.
No problem.
Okay, so in this water stripper, so we have removed the H2S, and we have the overhead. We will send it to the sulfur recovery unit, and the bottom we will cool it and send to the users or to the wastewater treatment. So this is more or less the process of this stripping section. What is the theory that we have inside this process? So the sour water that we receive is a solution with ammonia and H2S in the water You have here your tank in the refinery. That is this 17TK201 when you have mixed all this sour water from the different units. The H2S and the ammonia are dissolved physically, where the releasing of these gases is favored by decreasing pressure and increasing temperature of the solution. That is what happened in the stripper. The process is done in the stripper tower with the assistance of a reboiler, which vaporizes the water at the bottom. And let's see which are the main process variables in the unit. So the main process variables are the steam vaporization. This is the main variable which influences on H2S and ammonia removal. An increase in the vaporization and increasing the steam to the sour water reboiler will decrease the concentration of the strip water, the pressure at the top of the stripper. The lower the pressure, the better effect on removal of the acid gases. However, the pressure is set to send the sour gases to the sulfur recovery unit. So we cannot decrease it because we have remembered to send these gases to the sulfur recovery unit. The temperature control. The control of this temperature is done by cooling effect of the sour water stripper pump around train cooler. It is essential also that the temperature is between this range to prevent ammonia salt formation and to minimize water content. Remember that we have ammonia, so we can have some salt formation that we have to avoid because it can create a lot of problems in the process equipment. Oops, the test, no. Okay, these are the main process variable that we have in the unit. And I would like to share this PFD, and then we can see the. So here you have the different sour waters that comes to the unit and comes to this tank that is called the sour water stripper feed drum. In this tank, you have a special device here that will allow us to separate the hydrocarbon from the water. The hydrocarbon will get at the higher, like here, it will goes, I don't know how to explain here, but you have something that it will separate and it will allows you to separate the lower density hydrocarbons in this side and you have the water in this side. It is, I don't the name now, but it's like a baffle that you have that will allow the separation. So in this side of the vessel, you will collect the oil and you send to the slop tank, and in this size you will have the water. Okay, so in this you will have the suction of the pumps that it will send this oil that you can separate in this vessel and it will send to the slop tank. Okay, and here you have the water. In some cases, what it happens at the bottom or here, you can send the water from this compartment to this compartment, and you keep the hydrocarbon that is a lighter component here. It's not easy to represent in a PFD, but it's sometimes you have like a hold down in this like a wall here that separate the vessel into compartments, and then the water will go to this part of the vessel, and the oil as lighter will remain in this part of the compartment, and then you will have the suction drum will be located, that you will ensure that you have oil at the higher point of this vessel, of this liquid.
I think it's the data sheets will show a bit better
Yes,
the
yes.
arrangement and the PFD.
Yeah, but what is the idea? You separate, and you have the water from the bottom, and then you have an upper layer in this vessel, where you will get the hydrocarbons. Okay, from this vessel, you will go to the tank. Okay, that we have seen that we have a nice picture of your tank. Here you have nitrogen, because we have here a blanketed tank, and you have also a disposal of of gases to the incinerator in case you reach the pressure, a high pressure here in the tank. You will send it to the incinerator. Okay. These tanks also take into consideration the ambient conditions. When you cooled during nights, during colder temperatures, the pressure will go down, so you inject nitrogen to keep an appropriate pressure. But during summer and during the high temperatures, you will increase the pressure, then you can send the overpressure to the off gas. And also, of course, when you are working with the pumps, you have to replace the volume that you are sending with pressure here with nitrogen. Okay. So this is a fixed stock to our tower. That is the sour water stripper, the T101. This stripper is done by this reboiler. So with this water vapor, you will strip the ammonia, and it will goes to the sour water to the sulfur recovery, the sour gas to the sulfur recovery unit. Okay. It will collect also remember that we have two trains, and we will collect also this sour gas from train one. And here we have all our final product, that is the stripped water. The stripped water from the train 2, it will go to the crude distillation unit. Remember that it can contain some phenols, and it can be used in the some equipment on the desalter on the crude distillation unit without problem, but it cannot go to the other units. And here also we have a way to measure the pH of our water, to, if we require, if we have acid, very low pH, we can inject caustic to have the appropriate pH on the water. But I think that we have here also the temperatures that we have to work in the column. It is a simple process. Is only stripping with the water, vapor water that comes from the bottom of the column, as with the help of this reboiler. And we will have the H2S that we have removed from the water. We will have it here in the sour gas, that it will go to the sulfur recovery unit. We have seen also from the previous unit, these acid gases also going to the sulfur recovery unit. This is the sour water stripper. So the main idea is to remove the ammonia and the sulfur and the H2S that you have in this different sour water coming from the different units of the refinery. So I don't know if you have questions.
Yeah, let's check. Guys, do you have any questions before we finish off the sour water stripper unit presentation? Or if you have questions on the previous units for today's is also, I will hear your questions. Okay.
You know, Ahmed, if you call it, I haven't seen the data sheet, no? But maybe this is like an skimmer.
Yeah.
Okay. But I didn't see the data sheet, but we can.
Yeah, I think, or maybe the PNID slightly will give it the
Yes, yes, yes.
details.
Okay.
Yeah, so that's fine. Guys, you have no questions? So I don't see any questions.